Okay, so this is about observations of low mass habitable planets around nearby cool and low mass stars. And okay, and then there is the Watch subcommittee of the Breakthrough Initiatives which deals with this question. The mission of this subcommittee is to identify and characterize the targets for Starshot. So we are really looking into observations within 5 parsecs, not further away. And in the first phase, we are actually looking just at the Alpha Centauri system, Alpha Centauri A and B. And the main reason is that it's so much closer than all the other stars, is that there's actually something that with moderate investment and moderate instrument upgrades, already something can be done today. So we're trying to find a potentially habitable planet around these 2 stars. In a later stage, we will extend this range to 5 parsecs and look for biomarkers. And on the ELT instrumentation side, there are various venues that how this could be achieved. One is 10 micron imaging and spectroscopy of Earth-like planets around the early type stars, AFGK stars. There are not too many around within 5 parsecs. Another way would be near infrared imaging and spectroscopy. So this high contrast imaging around the M stars, and there's also the possibility to do 10 micron spectroscopy only around Earth-like planets, so without actually spatially separating. And that would be needed for the M stars, where you don't, even with ELTs, you don't have the spatial resolution. Also, another possibility is to participate somehow to radial velocity and astrometry missions, but this is not so well defined yet. So the 2 main activities of phase 1 is first a 10 micron ground-based imaging. So a 2 Earth radius planet around Alpha Centauri A or B would be seen at about 10 to the minus 6 contrast, and it would have a brightness of about 80 microjansky. So this is something that can already be done with an upgraded instrument, VLT Vizier at the moment, with adaptive optics and chronography, and 50 hours on-source integration. That means a 100-hour campaign. So this effort has been started, and the observations are foreseen for 2019. If you would like to go to even smaller planets, to about 1 Earth radius, then you would need the power of 3 large telescopes combined, and also better detectors, because the currently available mid-infrared detectors have a not so high quantum efficiency and have some noise issues that make it quite hard to achieve this goal, because it's quite challenging. The other activities is a small telescope put in space, is an astrometric mission. It's called Toliman. And here the idea is to look for relative perturbations in the orbit of the Alpha Centauri A-B binary. The thing is here that these perturbations are proportional to the mass ratio between the planet and the star. So it's for an Earth mass planet, it would be 1 part in a million. So that means for a 1 arcsecond orbit, we are looking for micro arcsecond effects. And this is even a factor of 10 more precise than, for example, the recently commissioned VLT interferometer gravity delivers. So this is a very challenging thing. But the team working on this has found a very innovative and interesting approach. It's a diffractive pupil. And here the first optical element produces the ruler itself in the image plane. So you see here that this pupil here produces all this little structure in the image, and this acts as a ruler. And you can then look for the relative motions between the 2 stars using this ruler. And all the optical components that are after the first one do not affect anymore this, because they affect the ruler in the same way as they affect the image. So place scale changes, optical distortions, and so on that vary with time are compensated automatically. So that's a very promising approach, and hope that it will work out. So beyond this phase 1, we want, of course, then to go a bit further. And from radial velocity surveys, we know that giant planets, for example, are more common around higher mass stars. So the higher the mass of the star, the more giant planets there are. And interestingly, the opposite trend seems to be the case from Kepler results for the low mass planets. So there seem to be more low mass planets around the low mass stars. So expectations are of the order of 1 in 4 or so in the habitable zone around the low mass stars. So we have the fact that terrestrial planets are more abundant around M stars, and we also know that most of our neighborhood stars are M stars. So that means that the nearby M stars are most promising to look for habitable planets. And in this plot here, you see the distance of habitable zones within 5 parsecs from Earth on the x-axis. And the size of the circle is the size of the habitable zone, and the color is the temperature of the star. So it goes from small red circles to large blue circles. You see Sirius down here, Alpha Cen at very small separations. But you see all these red circles here. And so there are about 40 of them. And if you have 1 in 4 for potential habitable planets, we can expect that there are about 10 potentially habitable planets that we could look at. And so these potentially habitable planets are planets where the temperature and surface pressure are suitable for liquid water. We don't know whether there's liquid water, and these can be found by radial velocity and transits. And we expect that, especially by radial velocity, most of these would have been found in a few years from now. The habitable planets, so that meaning the presence of water, liquid water is almost as difficult, or is as difficult or more difficult to detect than biomarkers, or like oxygen. So that's why we would probably skip this step and go directly to look for the biomarkers, so oxygen. And on the right plot, you see the spectrum of Earth. You see the 2 pronounced bumps of emission at short wavelengths, at long wavelengths, one in reflected light and one in the thermal emission of the planet itself. You see that both contain nice signatures, the oxygen band that we have heard about already at 760 nanometers. And there's also the ozone band at 9.6 microns. So these are the 2 interesting wavelength range to look for oxygen on exoplanets. So what does it mean in terms of observational requirements? In the near-infrared, so on this plot here, you see known exoplanets, plotted angular separation, flux ratio, so contrast ratio versus angular separation. Most of these are giant planets. But you also see Proxima b in this plot, for example, with contrast of 10 to minus 7 at 37 milliarc seconds in the near-infrared. And the TRAPPIST-1 system, which is as a higher contrast, so a more favorable contrast, but it is so close because of the distance to the star system. It is so close, the planets are so close to the star that even with an ELT cannot be resolved. The 10 5 parsec M-star habitable planets I was talking about are expected to be in this red located in this red circle. So what is needed is a contrast of about 10 to minus 7 to 10 to minus 8 at very small angular separations. And we need a good sensitivity because these planets are also faint. So they are about like 26, Proxima b is 23rd or 24th magnitude. So this is something that has to be taken into account. And in the near-infrared, noise is dominated by stellar residuals. So not by sky background, but by residuals from the star itself. In the mid-infrared, the situation is different. So here, the noise is dominated by sky and telescope background. So for example, typical values are 1,000 Janskis per square arc second. So that means even for an ELT Airy disk, we still expect 5 Janskis of flux simply from sky and telescope background. And that is more than we would get from the star itself. So even though the contrast is favorable, we cannot spatially resolve the planet from the star, but that's not really a problem because we can still observe the integrate and have almost the same noise as if we would optically separate them. So the technologies needed for these observations are actually 2 key technologies. The first one is high contrast imaging. I'm sure most of you have already heard about that. So that's a 3-step process. From the ground, the first thing is you would do extreme adaptive optics correction of the atmosphere. You achieve an Airy pattern. Then you put in a coronagraph. You remove the Airy pattern, and you are left with quasi-static residuals in the PSF. And then finally, you use differential method, for example, spectral methods. And that's a simulation here. To get down to the contrast level 10 to minus 6 to 10 to minus 9. And observations on sky with the sphere instrument at the VLT show that it's already pretty well matched with the simulations. So another key technology is the high dispersion spectroscopy. So here you use spectral resolutions of 100,000 and above to really resolve a molecular band into individual lines. And the main advantage of doing that, or there are several advantages for this high dispersion spectroscopy. And this is that the first thing is that you can look actually on the lines itself, and you do not need to consider the photons that are in between the lines. So you can throw them away, they only add noise. So in this way, the high dispersion spectroscopy actually can increase the signal-to-noise ratio, can be more sensitive than imaging or low-resolution spectroscopy. The other advantage is that the spectral lines shift with the Doppler motion of the planet along its orbit. And in this way, you can disentangle the motion of the planet from telluric lines in our own atmospheres on one hand, and you could also disentangle light from the star that is reflected off the surface, because the reflected light is also Doppler shifted along the orbit. So that's a very powerful way to separate between a planet and what's residual stellar light. And the combination of the two is extremely powerful. It's illustrated here. You have a high contrast image. You see a planet down there. And if you're not sure it's a planet, you look at the spectrum, and it looks very different than the spectrum of the quasi-static speckles. And this is how you differentiate and get to the contrast levels needed. So how do the two add up? It's actually as easy as it's expected that they simply multiply. So it has been shown, demonstrated already, that a factor 10 to the minus 4 can be achieved by the high dispersion spectroscopy. That means one good photon in a sea of 10,000 stellar residual bad photons can be detected with a high dispersion spectroscopy. And then the high contrast imaging gets rid of 1 part in 100,000 of the bad photons. So if you combine the two, you have 10 to the minus 4 times 10 to the minus 5. You can already now, in principle, go down to 10 to the minus 9 contrast level. There's a small caveat here, is that I've mentioned that we want to work at very small inner working angles. And contrast levels of 10 to the minus 3 or better at these very small inner working angles have not yet been demonstrated. So this is something that AO has still to show that it's capable of doing. And for that, it helps to have a close look at the XAO, Extreme Adaptive Optics error budget. You see here a plot for an ELT observing Proxima b. And in the analytical ideal case, you see that contrast level better than 10 to the minus 4 can be achieved at very small angular separations. And so the contrast is limited by mainly two error terms, which is a time lag and the chromaticity of the atmosphere itself. So chromaticity between wavefront sensing and observing wavelength. All these error terms are proportional to 1 over d squared, so 1 over the size of the telescope. And this is important for the next slide, is that this means that the observation noise is independent of the telescope diameter, both at the near-infrared, where you are dominated by residuals from the star, and in the mid-IR, where you are dominated by the sky background. The observation signal, of course, scales with the telescope size. And so if you combine these two, then you see that the time needed to achieve a certain signal-to-noise ratio goes with the 4th power of the telescope. So a 40-meter ELT can do a particular observation about 625 times faster than an 8-meter telescope. So that's an enormous gain brought by the ELTs. Another way to put it, that a 40-meter ELT can observe at 5 parsec with the same efficiency as an 8-meter can do at 1 parsec. So with the ELTs, we can extend our current observations to 5 parsec. So now I have just 2 slides of what we can do today already, so without having an ELT around. So Proxima b, oxygen detection. This is something that people have started to look into after the discovery of this planet. The angular separation is such that it can actually be resolved with an 8-meter telescope at short wavelengths, so in the oxygen band. So the contrast is very high. So you have to assume a very good AO correction at this angular separation, something that's still to be demonstrated. But if you can achieve that with realistic throughput assumptions, you could get a 5 sigma detection of oxygen in about 150 to 300 hours of telescope times. So that means 25 or 50 nights. So it's a significant investment, but it's something that you can start thinking about. So the instrumental upgrade would be here, that would be needed is an extreme adaptive optics upgrade for the current imager that we have at the VLT. And then you need a fiber relay to the high resolution spectrograph, or you build an individual small spectrograph that you couple directly at the instrument level. This is something that's been studied at the moment. So if you would then have the 40-meter telescope, you could, of course, do the same thing for M2Rs up to 5 parsecs that you could do for Proxima b right now. So you can do oxygen detection of all the M2Rs within 5 parsec. There's another very interesting venue, which is Proxima B unresolved. You could detect oxygen simply only with high dispersion spectroscopy. So the angular separation of 37 milliarcsecond is not spatially resolvable at 10 microns, even with an ELT. But if you just take a spectrum of the combined system, you can still, with the power of an ELT, detect ozone in about 20 hours. And 20 hours means like 3 nights of observation. I mean, this efficiency very quickly then drops when you go to systems that are further away. But at least for Proxima B, this is a very interesting perspective. So, and then I come to my conclusion. So inhabited exoplanets around nearby cool stars will soon be detectable by ground-based telescopes. Soon, within a few years, I would say. So in the combination of high contrast imaging with high dispersion spectroscopy is at the moment the most promising approach. And the O2 detection on Proxima B is already within reach right now, also pushing the envelope on the instruments. And the ELTs will be able to extend this range to 5 parsec and hopefully find the targets for Starshot. Thanks. Yes.
Hello. This is just a comment and a question. Because Mercedes was discussing about oxygen detection, and you also mentioned oxygen detection, I just want to point out that reflected light should be easier in a sense. So all the numbers that you do for oxygen detection, in principle, the spectrum of the star is reflected to the surface of the planet, which gives you a copy of the spectrum of the star, Doppler shifted quite a bit. Yes. And that's also what Lovi did. And if you do that, then you can get the albedo as a function of wavelength. I know that the albedo is not as nice as oxygen, but that's also a tracer of what the planet looks like at different wavelengths. So for example, you can compare with the albedo of the moon, albedo of Mars, albedo of a rocky planet with an atmosphere or not. And doesn't need so much, so all the numbers you have, you divide by 3 or 4, and that experiment in principle could be done that way. So I'm just saying that because it's a bit, if you make the numbers for O2 detection, you can actually get reflected light by a factor of 3 less observing time, things like this.
Okay.
Have you considered that, or what's your opinion on the topic?
So that was a comment. So the question?
Yeah, the question now is, have you done the numbers? I mean, I know I've seen the paper from you guys and
from Christoph Lovis, yeah. So no, me personally, I do not. I have not done the numbers. I know that the people in Geneva and also in Leiden are working on that. I guess it's an interesting comment that they will take into account, but I cannot say much more to that.
Yeah, no, I'm just saying that you have to sell that as well because it's a stronger.
So that it's not 150 hours, but just 50 hours. Yeah.
Yeah.
Sounds better, even especially if you use Espresso, which will take all 4 telescopes. So then.
Yeah. But the same for Mercedes for the detection.
Yeah.
You can, yeah.
Thank you.
One step after the other because it can be done actually. So.
Yeah. Jeff.
Thanks for this great talk. Marcus, when you consider the expected wavefront control on these hundreds of mirrors in the ELT, does it allow the full d² improvement that you described, or is there a multiplier that's gone into your estimates of the sensitivity?
Okay, so the ELT, the European ELT, will have 5 mirrors in the telescope rather than 3, like the VLT right now. Yeah, that's true, or 2 depending on the focus you look at. But so in the mid-IR, that can be an issue. That's true because the background is dominated by telescope mirrors, so mirror coatings are an important issue. I think in the optical, it will not make a huge difference.
Sorry, I was asking about this multi-segmented primary.
Multi-segment primary.
And whether your wavefront control is at the level where you will achieve the...
Sorry, yeah. No, I mean, we have run simulations already with the contrast that you can achieve, and at this angular separation, the multi-segment primary is not so much of an issue. I mean, the 10⁻⁵ contrast or 10⁻⁴ contrast that I've been talking about is achievable with the multi-segment primary.